Hello everyone, welcome back to Chem 51 or GOB Chemistry. Today we're looking at Chapter 15, which is Organic Acids and Bases. Specifically, we'll be looking at functional groups that contain the carbonyl group, the C double bond O group, specifically carboxylic acids, esters, and amides. We will look at physical and chemical properties of these four structures. And then in addition to that, we'll look at something that's related that doesn't contain the carbonyl, namely the amine functional group. And we'll again look at the physical and chemical properties of amines. Okay, so this is going to be an unavoidably slightly longer video, just because the chemistry is rich and it's hard to leave something out. We are going to have to leave some things out, but even then it's still going to be a little bit longer than usual. So let's go. Okay, so carboxylic acids, esters, and amides all contain this acyl group. An acyl group is just a carbonyl with an adjacent carbon. So if I can get my pointer working. Yeah, so we can see here the carbonyl, the C double bond O, the adjacent R group. That's what these three structures all have in common. So around that carbon, in the carbonyl, we have 120-degree bond angle. Let's see if I can annotate over here. Yeah, so we've got a 120-degree bond angle. Each of these angles would be the same. The structure shown on the left is an ester, because in addition to the alkoxy group shown, in addition to the carbonyl and the adjacent carbon on the left, we have the O carbon group on the right. So this is indicative of an ester functional group. A specific example of the ester shown here is methyl acetate. Again, they've called this methyl acetate because we have a methyl group here, and then this entire structure is acetate. So it's like that's the acetate part, and that's the methyl part. Okay. Okay, amides look similar, obviously, but instead of an oxygen to the right of the carbonyl, we have a nitrogen to the right of the carbonyl. So it's still a strong element. So we have an amide, again, a nitrogen bonded directly to a carbonyl's carbon. This is going to be important to us later when we look at protein chemistry. Again, we have the 120-degree bond angle. We have a polar structure. We can have flavors of amides. So similar to when we looked at primary, secondary, and tertiary alcohols, we have primary, secondary amides. So a primary amide is where you have, probably the easiest way to look at it is the amide, the nitrogen. Oh, I've got my black pen again. So it defaults to this weird black pen. Here we go. The amide, or the nitrogen, is bonded to one other carbon. That's one way to look at it. Another way to look at it is I have two hydrogens on my nitrogen. So that would be a primary amide. As you can see, I can now replace each hydrogen on the right with another carbon to make secondary and tertiary amides. So it's clunky changing slides because once I annotate, I can't click the slide. I have to go back into a different tool to click the next slide. It's very clunky. Here we go. So secondary and tertiary amides, we can again see we've replaced sequentially the hydrogens on the right of the amide with carbons. Let's go back to my annotation tool. So again, the nitrogen now has got 2 carbons, so it's secondary. The nitrogen has now got 1, 2, 3, so it's tertiary. Again, you can either look at it as you've got more and more carbons, or you can have it, you've got fewer and fewer hydrogens. So that's one way you can look at that. It will not let me click a slide unless I click about 3 buttons. Okay. We can have, so they are acyclic or linear structures. We can also have cyclic structures. So a cyclic ester is shown above. It's known as a lactone. So a lactone is just generally a cyclic ester. We again can see it's an ester because we have the carbonyl group. Here I am again with my red pen. So we've got the, no, that's the black pen, the red pen. There we go. So we've got the carbonyl, the adjacent oxygen, so we know it's an ester. Well, actually, it's not just because it's an adjacent oxygen, so let's be careful. Let's get the eraser on that adjacent oxygen. So to be an ester, you have your carbonyl, you've got your adjacent oxygen, but you also need a carbon. So that's really what we need to be an ester, a carbonyl with an OC on one side. So we have the OC here. So that's what makes it an ester, and it's all linked in on itself. So we have a cyclic ester, we call that a lactone. And a cyclic amide, we call a lactam. And you can see here, it's an amide because it's got the carbonyl. It's got an adjacent nitrogen. So that's what makes it an amide. And you can see that structure right here. Links in on itself, so we have a lactam. Okay, so let's keep it moving because there's a lot to get through. Okay. Carboxylic acids are another type. So we've looked at esters, amides. Carboxylic acids kind of start off looking like esters, but we have this H rather than a carbon. So just to compare an ester with a carboxylic acid, carbonyl, O carbon versus carbonyl, O hydrogen. So we're looking at the latter here, carboxylic acid. It's an acid, it will have a lower than 7 pH. It's a weak acid, but it's an acid. And what happens is we end up breaking this bond and we donate H plus. So it fulfills the criterion that it's a proton donor. An acetic acid is an example of a carboxylic acid. And this is the main ingredient in vinegar, so you probably all can now visually smell what this smells like. You know, the vinegar has a very bitter taste, so that would be characteristic of this type of acid, very pungent, bitter tasting chemical. Okay, so far everything has had a carbonyl, and for that reason we can learn a lot about similarities of these compounds, at least based on structure. So we can see the carbonyl looks kind of like a Mercedes-Benz symbol. It has a 120-degree bond angle. It has a polar, a net dipole that points along the direction of the carbonyl bond. So from the carbon, which is delta positive, with respect to the oxygen, which is delta negative. That means that in terms of its chemistry that we're about to explore, things that have electrons can attack the carbon because the carbon is electron deficient. Things that need electrons can be attacked by the oxygen because the oxygen is electron rich. Again, nomenclature rules here is not super critical, at least for my class. But you're going to see these names in textbooks, on questions, in assessments. So it's good to at least be familiar with what the name probably is, even if you're not a faithful scribe of the names to begin with. Much better to know the chemistry of something than the name of it. Okay, so carboxylic acids always have this ending oic acid, so they are in general carboxylic acids. So for example, carboxylic acid with 2 carbons in it would be ethanoic acid. You have methanoic acid, ethanoic acid, propanoic acid. So you see this suffix oic acid to represent the carboxylic acid. Here's an example. We identify the longest continuous carbon chain that contains the carbonyl of the carboxylic acid. Here it contains 6 carbons, so it's hexanoic acid. But we notice it has 2 methyl groups with respect to the carbon backbone on carbons 4 and 5. The carbonyl carbon is by definition carbon 1. So the 2 methyl groups on carbons 4 and 5 just become 4,5-dimethyl 4,5-dimethyl hexanoic acid. Okay, in addition to IUPAC names, we also have some common names for carboxylic acids that you'll see because they're used frequently. So acetic acid in the middle is the main one. You can't get through a GOB class without bumping into acetic acid at some point. Formic acid on the left is where we've replaced that methyl group with just a hydrogen. And then benzoic acid on the right is where we've replaced the methyl group with a benzene ring, which is an aromatic group that we saw in a previous video. So these are old non-systematic names, but very commonly used compounds. So you should be aware of the names. There is I would say definitely an older naming convention that's going to be useful to us, especially when we look at fatty acids later in our course, and specifically when we look at beta oxidation of fatty acids, which is going to come up for my students next week. And that is to label, it's also going to come up, I guess, in protein chemistry when we look at alpha amino acids. So the alpha and beta carbon, so we look at the carbonyl on the right, and then which is by definition carbon 1. And then the carbon that's immediately adjacent to carbon 1 is the alpha carbon, annotated here. The carbon that's immediately adjacent to the alpha carbon is the beta carbon. So that's pretty straightforward. And again, this will come up, this alpha and beta labeling of carbons in groups containing a carbonyl, it will come up in amino acid chemistry later, and it will also come up in fatty acid chemistry later as well. Because of the presence of the carbonyl group in these structures are polar compounds that can or cannot be soluble in water. It really depends on how many carbons there are. So you're polar, again, because you have a dipole motif in your structure. That carbonyl has a dipole. And depending on the type of carbonyl you have, you can form different types of intermolecular force. So for example, the structure shown here, let me get my pointy thing. The structure shown here is an amide. We've got the, in case it's not clear where I'm pointing down here. With the red marker, zoom please, the red marker. Thank you. Yes, thank you very much. Okay, so we have the carbonyl, the nitrogen. So that's an amide. And we can see two amides, so it's the same structure, two adjacent molecules of the same structure, just interacting with each other. We've got the oxygen here of one carbonyl group on one molecule, interacting with the hydrogen on the nitrogen of an adjacent molecule. So this is a hydrogen bond because we've got an eligible hydrogen because it's directly bonded to either nitrogen, oxygen, or fluorine. And it's interacting through space with either a nitrogen, oxygen, or fluorine. So if amides can hydrogen bond, they're going to have a relatively high melting and boiling point compared to alkanes of a similar mass. Clearly, to hydrogen bond, you need an eligible hydrogen. So primary and secondary amides have at least one hydrogen on their nitrogen. Tertiary amides don't. They have only carbons on their nitrogen. So tertiary amides are incapable of hydrogen bonding and would have a substantially lower melting and boiling point for a similar mass. Okay. Carboxylic acids, if you recall from a previous video, if you take a primary alcohol like 1-propanol shown on the left, we can oxidize primary alcohols to give aldehydes. Then we can oxidize aldehydes further to give carboxylic acids. And you can see that the physical properties for a similar weighted molecule increase if you oxidize the alcohol all the way to the carboxylic acid. And this is just because you've added an extra oxygen, so you've added the possibility of more intermolecular forces, more hydrogen bonding. The alcohol, at least the one shown on the left, only has one oxygen and one eligible hydrogen to hydrogen bond with. The molecule on the right has an eligible hydrogen, but now it has two oxygens capable of hydrogen bonding. Likewise, or in a similar vein, on the left we have an ester. So you've got that carbonyl with the adjacent alkoxy group. A boiling point of that structure is 58 degrees Celsius. You can convert that into a carboxylic acid of a similar weight. So those two structures are constitutional isomers of each other. So let's at least reflect that real quick. I think you click on the same thing 7 times and then it will, no, keep clicking. Keep clicking. Yes, there you go. All right. So we've essentially taken this methyl group and we've shoved it over here. So these are constitutional isomers. So looking at these two constitutional isomers of each other, we can see that the carboxylic acid has more impressive physical properties. Again, the ester on the left does not have an eligible hydrogen to hydrogen bond. The carboxylic acid on the right does have an eligible hydrogen, and that will be a stronger intermolecular force. So the strongest intermolecular force capable for the ester on the left are dipole-dipole forces. Hydrogen bonds are stronger only the molecule on the right can do hydrogen bonding, so it will have more impressive physical properties. What do we have here? Again, this is just echoing something we said on a previous slide. The ester on the left, no hydrogen bonding. It has a certain physical property. Tertiary amide in the middle. Also, no eligible hydrogens to hydrogen bond with. We don't have a hydrogen directly bonded to either the nitrogen or the oxygen. So it will have a certain value. Compare the middle value with the primary amide on the right. Clearly, we have hydrogen bond capabilities, which substantially raises the physical properties of that primary amide. So if you had to rank these, so they're roughly similar mass, approximately similar mass. The tertiary amide, how can we argue that that's substantially more physically impressive than the ester on the left? Well, they both can form, well, again, we have to be careful how we say this. So the tertiary amide in the middle cannot hydrogen bond with itself, but it could form hydrogen bonds with something that did have an eligible hydrogen, like water. So that's not what's causing its physical properties to be high here. We're assuming it's just interacting with itself. It will just form dipole-dipole forces, and they will just be stronger than the dipole-dipole forces made by the ester on the left. So that's what we can see. This slide is just for giggles. I mean, it has the word dirty sock and locker room in. So read it, but I and nobody else is going to ask you what chemical has the smell of locker rooms. So moving on. Okay, so carboxylic acids are acidic. They have a low pH, lower than 7. They're weakly acidic. And they're acidic because they donate the acidic proton. So labeled red here, they break that they break the oxygen-hydrogen bond when exposed to water, and they generate the hydronium ion, which is that ion on the right. So let's see if my system will let me write without clicking it 17,000 times. Yes, it will. All right, hydronium ion. So this essentially is what happens when you, so initially we're going to break this bond. The oxygen keeps the electrons and the hydrogen gets left in the dust, but the hydrogen rapidly is scavenged by water, and that's going to generate the hydronium. So you add H plus to H2O and you generate H3O plus. Again, it's a weak acid, so only a small percentage on average of the molecules will do this, certainly less than 50%. So although it can be represented in its ionic form, the major species is going to be the molecular form. So that's typically how we represent carboxylic acids, not as the free ions on the right, but as the intact molecule on the left. Okay. We can interact a carboxylic acid with a base and perform a neutralization reaction. So when we neutralize an acid with a base, we form a salt and water. So this is a type of chemistry we can do with carboxylic acids. It's called a neutralization. Acid plus base to give a salt plus water. So in this specific example, acetic acid is the acid, the base is sodium hydroxide, the salt is sodium acetate, and water is water. So as you can see here, the H is going to go with the OH minus to make H2O. And the Na plus is going to come over here with the acetate to make sodium acetate. So in general, neutralization is a type of double displacement. So it's a specific type of double displacement. And in general, a double displacement, you have a compound AB, another compound CD. You can form AD plus CB. So essentially, you have cation exchange. So A takes D and C takes B. So clearly here, we've just exchanged the H plus on the acetic acid with an Na plus from the base. So this is a type of chemistry carboxylic acids can do. So, if you cast your mind back to the alkane video, definitely we can do a lot more interesting chemistry than just burn this as a fuel. So much more high value product. So if we do this, so why might you do this chemistry? You can see here one use is to increase the solubility. And this type of chemistry will be done in, for example, pharmaceuticals. You can make pharmaceuticals more water soluble to help with the distribution throughout the body, make it either more bioavailable intravenously, more bioavailable orally as a topical medication, or sorry, as a topical medication maybe, or just for oral ingestion. Okay, so if we take octanoic acid, which is a carboxylic acid, we see the suffix oic acid. Octan just means there's 8 carbons in a chain. It's insoluble because we just have a lot of carbon. We can treat that with a base, perform a neutralization. We can make the sodium salt or sodium octanoate and water. So that's our neutralization reaction. We've increased the water solubility and it's actually water soluble now. So what changed? Well, on the left, the strongest intermolecular force, for the most part, ignoring the fact that there's a tiny bit of ionic nature to the carboxylic acid, by far the most representative intermolecular force on the left is the hydrogen bond, which is strong, but there's something stronger. On the right, we have free ions. So we can have ion dipole forces. Ion dipole forces are stronger than hydrogen bonds. Ion dipole forces are the strongest type of intermolecular force. So the ion is obviously either the acetate or the sodium. The dipole is the water. So water can dissolve sodium octanoate because the water provides the net dipole. The sodium octanoate provides the ions, and the two can interact and form ion dipole forces. And this drags the sodium octanoate into solution. Okay, one useful practical application of this type of chemistry are soaps. So for several thousand years, we've been having our soapy bubble baths. No, seriously, the invention of a way to clean yourself dramatically increased human life expectations, because for the first time, humans were able to be clean, although history shows that they often chose not to or couldn't afford to, but at least it was possible. So a soap is a molecule that partially likes grease and grime and partially likes water. So we have one molecule with different components of the same molecule forming different intermolecular forces. So we have what's called a polar head, which likes water, and a non-polar tail, which doesn't like water, it likes grime and grease. Here's an example of a soap molecule. Again, we have this polar head with all of its hydrogen bonding capable oxygens, and it's got the iron here, so you can form iron dipoles. And then we've got this long, greasy carbon chain, this alkane chain that only likes other alkanes, which are the major constituents of grease and grime. So the head sticks into the water, the tail sticks into the grease, and locks them together. It basically locks water and grease together so that you can flush the water away and therefore flush all the grease away too. In solution, these structures self-assemble into what's called micelles. So you can see here one of these structures that if you look closely, you've got a green sphere. That's the polar head of the soap molecule. You've got this long brown chain. It almost looks like a matchstick. The long brown chain is the greasy non-polar tail. And they self-assemble into spherical micelles, where all the greasy chains kind of cluster together in the interior. And the water molecule preferentially interacts with the polar head via its hydrogen bonding and what have you. So water helps mold this thing into a spherical micelle. And when you either wash your dishes in water containing this stuff or rub your body in liquid soapy water containing this stuff, any grease on your dishes or grease on your body will be trapped in the interior. It will get locked inside here, and then you can flush this away with the water, etc. If you get soap scum around your bathtub, it's because these things have been present and they've popped open. So if these become unstable because they're so full of grease and grime, they can occasionally pop open and splatter all on the side of your bathtub. And that's what soap scum is basically. Or in your sink, if it feels slippery and grimy after a while, you've got micelles splattered everywhere. So you'd eventually have to get something harsher than soap to clean that, some kind of detergent. There are biological equivalents of this. This essentially is similar, not identical, but similar to how you can transport oily materials through your body, through your bloodstream. They're related structures, they're not identical, but we'll get to that in another video. Here you can see a cross-sectional view of a micelle. You've got the polar heads interacting with water. You've got the non-polar tails interacting with the payload of grease and grime. And we've got this, whereas water wouldn't interact with the grease, we've kind of got this intermediary in the form of soap molecules. We can exchange one group for another. So we can basically interconvert these functional groups via substitution. So in this cartoon here, we can see the Z group is substituted by the Y group. And the Z can be either an alcohol OH an ester, an alkoxy group, which would make the compound an ester, OR, or an NR2 group, which would make the carbonyl an amide. So carboxylic acids can become esters and amides. So basically what this is saying, if I would rephrase it, you've got esters, amides, and carboxylic acids. Esters, amides, carboxylic acids. Esters can be converted to the other two. Amides can be converted to the other two. Carboxylic acids can be converted to the other two. That's what the slide is saying. Okay, for example, we have a carboxylic acid here on the left. We have a primary alcohol as the substituting group, and it's nicely color-coded, so it's very easy to track what's happening. Essentially, we can replace the red alcohol group on the carboxylic acid with the blue alkoxy group on the alcohol to generate on the right an ester and water. So we've literally replaced the blue and the red groups, and we've converted the carboxylic acid into an ester. Oh, incidentally, in this course and in GOB in general, the mechanism is not that important to us. Just, so we can just hand wavy, just exchange the groups and not worry about exactly how does it happen. That would be for a more advanced course. So it's okay at this level to be a bit more hand wavy than we might be in a different course. In this example, we have an alcohol, again, another a carboxylic acid on the left, and an alcohol on the left as well with the blue motif. And we can exchange specifically this methoxy group in blue to make this new ester and water. So this is just a specific example of the more general case on the previous page. In general, if we're making an ester, we can refer to this as an esterification. That's probably about as much information as we need in this course. In a similar way, we can make amides. So we have a carboxylic acid on the left. We have an amine, which we'll look at. Amines as a chemical motif later in this video. It's the last topic we look at in this video. But an amine just has a nitrogen with single bonds on it. And we can see that we're going to exchange the red motif on the left with the blue motif. And we form an amide where we have the nitrogen directly bonded to the carbonyl and water. So carboxylic acids can be substituted with amines to produce amides. A specific example here, we have acetic acid and ammonia, and we can make a primary amide and water, which has not been written, but there would also be a water molecule here. So essentially the water would be made from the H and the OH. Okay. On the top, we have production of a secondary amide on the bottom, we have production of a tertiary amide. Clearly, it depends what type of amine you have. If you have a primary amine, which is the one on the top, it's just a nitrogen with one carbon on it, you can form a secondary amide. If you have a secondary amine on the bottom with a nitrogen, which is a nitrogen with two carbons attached to it, you can form a tertiary amide. So you can control the type of amide you want based on the type of amine you use to make it. Esters can further react with water to produce carboxylic acids. So this is the reverse process that we saw earlier. Earlier, we saw carboxylic acids being esterified. Now we're seeing them being hydrated, essentially. So we can have an exchange of the red alkoxy group with the blue hydroxy group to form the carboxylic acid again. How you do this is not really relevant to us. The fact that you can do it is what's relevant to us in this class. Specific example, we have ethyl propanoate, which is an ester. We add water to that. We split water up in a hydrolysis reaction, and we exchange the blue and red colored motifs here to generate the primary alcohol again and a carboxylic acid. Again, the mechanism is irrelevant, so I wouldn't worry too much about the acid catalyst here. Who cares for our purposes? But we have an amide, so here it's a secondary amide. That nitrogen, in that red nitrogen at the top left, has two carbons attached to it, the methyl group and the carbonyl itself. We can add water to that to generate our carboxylic acid, and we form an amine salt, which would be soluble in water. So here's another specific example where an amide is being added to water and it's converted into a carboxylate anion with the base ammonia. So these are examples of acid-base reactions or neutralization reactions. Okay, so the final stretch of this video is to look at amines. So we started to see amines used here to make amides. Amines are going to be very useful to us next week in this course when we look at alpha amino acids and protein structures. So whereas an amide has a nitrogen adjacent to a carbonyl, an amine is just a nitrogen that forms three bonds and has a lone pair. You can have primary amines where the nitrogen has one carbon. You can have secondary amines where the nitrogen has two carbons. You can have tertiary amines where the nitrogen has three carbons. Clearly, primary and secondary amines, because the hydrogens are directly bonded to nitrogen, they're capable of hydrogen bonding. Tertiary amines, there is no direct bonding between nitrogen and hydrogen. They are incapable of hydrogen bonding, and that's going to affect their physical properties. We can, unusually because of that lone pair, we do have a fourth option with amines. That lone pair can be cast off to snag another either hydrogen or carbon, so we can get a quaternary amine where we've lost the lone pair on the nitrogen. We formed a fourth bond using the lone pair, but in doing so, we've pushed our electrons away from ourselves, and we've therefore picked up a positive charge. So this quaternary amine has a unique structure, and it has a positive charge, and it's sacrificed its lone pair. So very, very altruistic. What are the before I skip ahead, what are the consequences of this? Well, now we have an ion, right? So now we're capable of forming ion dipoles, which can not only increase our solubility, but it can, we now have to worry about being an ionic compound. It will probably make you a solid. If we get rid of all the water molecules, we'll be a solid rather than a liquid or a gas. And in water, we'll probably have high solubility. Okay, the structure around the amine, again, it's based, if you cast your mind back to our VSEPR lecture, then we are based on a tetrahedral electronic structure, but the geometry is trigonal pyramidal because we kind of don't reflect on the lone pair. So we just look at what's left without the lone pair, and what's left is a three-sided pyramid. So we have this, it's not exactly 109.5. This bond angle comes from a pure tetrahedron, but that's good enough for us in this course. It's approximately 109.5. And it's polar, so we would have a net dipole pointing from the base of this trigonal pyramid up through the lone pair on the nitrogen. As we said before, the primary and secondary amines are capable of hydrogen bonding. I guess quaternary amines as well if they have a hydrogen, but really the intermolecular forces of a quaternary amine would just be dominated by the fact that it's ionic. So when you look at intermolecular forces, you really need only focus on the strongest type of intermolecular force. If you're capable of hydrogen bonding, you don't really worry about the dipoles. If you're capable of ion dipole bonding, you don't really worry that much about the hydrogen bonding anymore. Okay, if we compare the physical properties of this ether on the left with an amine in the middle and then an alcohol on the right, they get increasingly more impressive. Ether, strongest intermolecular force is dipole-dipole, no hydrogen bonding. The amine in the middle, roughly the same weight as the ether, more impressive because it can hydrogen bond because of its nitrogen. The alcohol on the right, more impressive again. It can hydrogen bond, but it forms stronger hydrogen bonds because the oxygen is more electronegative than the nitrogen. And so what's causing the hydrogen bond is more extreme in the case of oxygen than it was in the case of nitrogen. We can see here tertiary amines are incapable of hydrogen bonding, lower physical properties. Here we have a secondary amine. It does have a hydrogen bond capable hydrogen, so more impressive physical properties as a result. We saw that carboxylic acids were acids. They are proton donors. They can form hydronium. Amines are bases. They are proton acceptors, and they can form hydroxide. So an amine can use its lone pair to capture a proton from water, forming NH4+, which is an ammonium ion, and we're left with OH- as the thing that's going to make ammonia a base. So if you were to add an amine to a carboxylic acid, that would be a neutralization because you have an acid and a base reacting together. This essentially is the chemistry of proteins, which we'll see in a future video. Here, as an example, we have an amine, which is a base, an acid. In this case, we have carboxylic acid, which is essentially the acid in your stomach. The lone pair is going to capture this proton and make a quaternary amine here. And the base that's left is the conjugate base that's left is just a chloride anion, which has lost its charge somehow. So let's put that back in. So this is not chlorine, it's chloride. Okay, so it lost its charge somehow. Okay. Almost there. If you've survived this long, we are almost there. Very long video. Okay. So amines, once they undergo neutralization, they form ammonium salts. And that's the quaternary amine structure. In general, it's an ammonium salt. So again, this is mainly just vocab. So there's a lot of different names for chemicals. And if you don't know the name, eventually, names are not that useful in of themselves. They're useful if they spark a train of chemical thought in your brain when you hear the name. Like if I hear the word predator, it sparks a response in me. If I hear the word chocolate, it sparks a response in me. If you hear the word, as a chemist, if you hear the word ammonium, it should start a chain reaction of thoughts in your head. That's the use of names. Not just learning NIST and impressing people in Starbucks with how many names you know. So again, we can increase the solubility of an amine. So here, octylamine is water insoluble because there's just too many carbons. Nitrogen can't quite interact with water well enough to drag all of these carbons in with it. Remember from a previous video, we said roughly for every 6 or so carbons you have, you need at least 1 nitrogen or oxygen to help pull the carbons into water. Well, 8 is just too much, so the whole thing is insoluble. But if we neutralize this amine with an acid to produce this quaternary amine structure here, we now have the extra advantage of having ion dipoles. So here on the left, we just had hydrogen bonds. It just wasn't enough. Now on the right, we have ion dipoles, which are stronger and which are enough to drag all these carbons into solution, and we have a water-soluble compound. Okay, we are now able to conclude this video. So see you in the next one.